differentiation from first principles. I want to have a look at how it actually works and see if we can sort of make things seem a little bit more simple, because differentiation is really quite easy. Let's have a look. I want to take a look at how we work out the gradient of basically some sort of linear function. And for this, let's take a look at a function which is y equals 3x plus 2. Let's see what we've got with this graph. Well, what do we know when we try and consider this straight line? Well, if we've got this y equals 3x plus 2, we know various bits and pieces about this. So let's just put in some marks, and I know this line is going to cross here at 2, and the gradient for every one of these I go across, we're going to go up 3. And every one more I go across, I'm going to go up 3. So here I've got my straight line of y equals 3x plus 2. Went the wrong way. Right. So let's see if we can calculate the gradient. Well, how do we go about trying to calculate the gradient for this? Well, it's not really that difficult. We could start off with the idea that this gradient is the rise over the run, and that means the gradient is going to be whatever the rise is. So let's consider this point to that point. So this is the point 2, and this is going to be the point 5. So we've got a rise here of 3 over the run of 1, and 3 over 1 is the same as 3. No matter which points we choose, the value of the gradient is always going to be the same. It's always going to be 3. And that's the feature of some sort of straight line. If we look at the values of some of this curve, and let's take our values of x from -3 to, let's go to +3. So here we're looking at the value of 3x, which is going to be -9, -6, -3, 0, 3, 6 and 9. We're going to take away 2 from each of these, so we're going to get, for y equals 3x minus 2, we're going to get -7, -4, -1, 2, 5, 8 and 11. If we look at this table of values, we notice that for every unit of x, here we have an increase of 3. So 7 to 4 is 3. If we look at minus 4 to minus 1, it's 3. If we look from 5 to 8, it's 3. In other words, y is increasing at a rate of 3 units for every unit increase in x. And we'd say that the rate of change here of y with respect to x is 3. And we can see that the gradient of the straight line is the same as the rate of change of y with respect to x. Now, none of that's really very surprising, really. So, how about if we look at this instead of a straight line, we look at this as instead a curve. So for any curve, if we choose 2 points, so let's just go ahead and try and choose a curve. If I choose any 2 points, and we'll call this one P, and we'll call this one Q. Now onto the ruler, that I can get some sort of straight line here. Whoops, press the wrong button. So I've got my straight line, and as Q here tends towards P, then what I find is that this point is changing, and if I draw perhaps a slightly better curve, as my points change here, that as I bring them closer together, then this point that I'm trying to make here, this is P, this is Q, as I'm bringing them closer together, this line becomes a tangent. So let's look at a simple example of this, and the easiest one I can think of, and the one that I was always taught, was y equals x squared. So let's look at this graph y equals x squared, and we'll have a look at some values of x. So we'll do the same as before, we'll do minus 3 down to plus 3, well, probably up to. And if we look at y equals x squared, then we're looking at 9, 4, 1, 0, 1, 4, 9. Now, if we look at the change in y with respect to x, if we take these two values here, then we're seeing that y is decreasing from 9 to 4. So it's reducing by 5 units. But if we look at the next two, from 4 to 1, it's reducing by 3 units. And then we look at this, it's 1 unit, so it's reducing by these. I'll put a minus. And then it's going back up again. So our gradient here is basically not changing constantly as we saw in the linear function, but here we're finding that the rate of change of y with respect to x is basically not constant. So how are we going to try and do this? So what we're going to try to do is we're going to try and look at my board stuck to the table there. If I draw in some sort of curve here, then if I look at a point here, P, we're going to try to have a look at this change here. So we're going to calculate the rate of change for any point on this curve. This is going to be, in this case, y equals x squared. It's going to be defined here as the gradient of the tangent at this point P. So the gradient of a curve of any function, y equals f of x, at a given point is defined as the gradient of the tangent at that point. Now we can use this definition to calculate the gradient at any point. So let's try and consider what's going to happen on this graph. So let's take a look at 2 points on this line. I've got a point Q and I've got a point P, and if I join up P and Q, we've got here a straight line. Now what we're going to do is we're going to imagine that Q is quite close to P, and if that's true, then what we can do is we can drop down a perpendicular from Q, and we'll join that up with the horizontal line from P, and we'll give this new point a point R. Now here we've got a right angled triangle. So what we know is, if we've got this as a graph of y equals x squared, if this point P has an x value of 3, then the y value here has got to be x squared, which is going to be 9. And our point Q is going to be a point that is basically nearby. So let's imagine Q has a different distance to P. So for the bottom of this triangle, this distance here is going to be PR. Let's have a look and see what's going to happen here. So for the distances of PR, I'm just going to draw in our little triangle just to remember what we're talking about. Got our point P, which is at 3, 9. This is our point Q, and this is our point R. So let's imagine that PR for a moment is going to be, the distance to Q is going to be 0.1. Well, let's have Q a little bit closer. Let's imagine it's going to be at 0.01. Let's imagine Q a little bit closer still. Let's imagine this at 0.001. Perhaps even imagine this even closer, 0.0001. Let's decide on then what is this value of Q going to be. So if P is at 3, 9, then we've got this small value of Q, so it's going to be, for our x coordinate of Q, this is going to be 3.1. In our other example, it's going to be 3.01. It's going to be 3.001. And in our final scenario, 3.0001. So this is a value of whatever it's going to be, 3 plus whatever PR was. Let's see if we can calculate y. We're going to work out the y value of Q, and that's the square of each. So 3.1 squared is going to be 9.61. 3.01 squared is going to be 9.0601. This is going to be 9.006001. And finally, this is going to be 9.00060001. So, what is the change in y for each of these values of QR? So let's see what QR is going to be. Well, QR is going to be 9, because it's the value there, 9 minus each of these. So this is going to be 0.61. This one's going to be 0.0601, 0.006001, and this is going to be 0.00060001. So let's see what's happening here. Well, what it appears to be happening here is this value is tending towards 0. So our change is 6. And 6 just happens to be 2 times our original value, 3. Perhaps it is coincidence that 6 is 2 times 3, where 3 is the x value at this point. Well, let's see what we can do about doing this in sort of general. So let's have a look at this as a sort of a more generalized equation. So let's draw in my graph. And let's draw in my x squared graph. Now, I've got the equation y equals x squared. Let's put 2 points on the curve. We're going to have point P and we're going to have point Q. Q is going to be a very short distance away from P. So let's drop perpendicular down, and again we're going to have R as we had before. We've got the coordinates of P, and this is going to be x, y. We're going to make it a general. It's the same basic triangle as we had before. We've got this line up here, and what we're going to do is we're going to bring Q towards P. We're going to basically look at this point here. Now, where is R? So what we're going to do is to work out where R is, we're going to increase X by a very small amount. And what I'm going to do is I'm going to call this delta X. Now, delta X does not mean delta times X, but this is just a symbol, and it's a symbol for a small amount. So I could have given this any particular symbol, but instead we're going to call it delta X. So let's look at this triangle. So I'm just going to redraw this triangle just so we can see the triangle. We've got P, got Q, and we've got R. P has the coordinates x, y, and Q is going to have the coordinates of x plus a very small amount of x, which we said is going to be called delta x. And it's going to have a small increase in y, which we're going to call delta y. So y plus delta y. So this distance here is delta x, and this distance here delta y. Let's do some calculating. We know this is the curve, the equation of y equals x squared. So at the point Q, we know that y plus delta y equals x plus delta x all squared. I've just written this equation out again. And let's now see if we can multiply this out. So y plus delta y is going to give me x squared plus 2x times delta x. I'm going to put it in brackets just to try and convince you that this is a term that goes together, plus delta x all squared. So what else do we know? Well, at the point P, we know simply that y equals x squared. And we know at Q that y plus delta y equals x squared plus 2x delta x plus delta x squared. So now if we know that simply that y equals x squared, then basically delta y must be equal to all the rest, so that delta y is going to equal 2x delta x plus delta x all squared. I want to work out the gradient of PQ. That's what we're after doing anyway with this problem. So let's take that. So let's take our gradient of PQ, which we know is the rise over the run. That's going to be QR divided by PR. QR is the change in y, which we're going to call delta y, and PR is going to be the change in x, which we're going to call delta x. So our gradient is going to be delta y divided by delta x. Now I've already got expressions for delta y and delta x. Delta x is simply delta x, and we know that delta y is 2x times delta x plus delta x squared. So delta y over delta x is going to be equal to 2x delta x plus delta x all squared, the rise over the run, and delta x is simply delta x. Now delta x here has a common factor, so let's see if we can take that out. And that's going to give me 2x plus delta x times delta x all over delta x. Now we know that delta x is a very small positive value, and so we can cancel it out. So now we have that delta y over delta x is going to equal 2x plus delta x. Now we have to remember what we're doing. We're trying to calculate the gradient of the line PQ. As Q becomes nearer and nearer to P, so this delta x is going to become nearer to 0. It's tending to 0 until these points become so close that PQ becomes equal to the tangent at P. So as delta x becomes smaller and smaller, we are approaching 2x. Now we need to write this mathematically, and to write this mathematically we need to use some mathematical symbols for this. So I'm going to say that the limit of delta x as it tends to 0 of delta y over delta x is, in this case, the limit of delta x as it tends to 0 of 2x plus delta x. And that's going to tend to 2x. And this is almost the same as our previous example we said, because we said there that 6 was 2 times the position of x, which in that case was 3. Now we can look at this for lots of different positions of x. We can try it at 3, 4, 5, but we can try and do this more generally, and it's a bit of a pain trying to write all this out. So instead of writing this limit as delta x tends to 0 of the change in y over the change in x, we're going to represent this as a symbol, dy by dx. And in this case we're going to say that dy by dx equals 2x. So we took our line y equals x squared, and we have then differentiated by first principles, and we can say that the differential, which is the gradient of the tangent at any point, is equal to 2x. Now, how can we do this? Well, a way of trying to do this is to take our function y equals x squared, and we take this number and we multiply that by the x. So dy by dx is going to be 2 times x, and this value of x will decrease by 1. So we take our number, put it down here, and our x decreases by the value of 1. Let's look at a particular example of this, and we'll just grab a couple of numbers that we can have a quick look at. Let's take, for instance, x to the 8. So y equals x to the 8. So for this one, dy by dx will equal 8x, and the value of the indice will decrease by 1. And that gradient at that tangent will be 8x to the 7. If we have y equals x to the 4, then this will become dy by dx equals 4x cubed. We'll try one more. Y equals 1 over x squared. Now, I'm not very clever, I can't differentiate that, so I'm going to change that into x to the minus 2, which is just another way of writing this. Later, we'll look at how to differentiate this in one go, but this is y equals x to the minus 2. The same rules apply, and we get minus 2x, and we take away 1, so this becomes to the minus 3. And if I want to try and put that back as it was, this is going to be minus 2 over x cubed. Either of those are really right, but sometimes it's polite to put this back in the format that you were given it. A slightly harder differential equation might be if I was given y equals 4x cubed. If we look at 4x cubed, then the same rules are going to apply. Dy by dx is going to be, we take here 3 and multiply at the front, and there's a 4 there, so we multiply them together. So that's going to be 12x, and this number decreases by 1, 12x squared. Well, can we make anything a little bit more difficult? Yeah. They're going to bound to give you something a little bit harder. So we might get y equals something like x squared plus 3x. So what are we going to get here? Well, dy by dx is going to become 2x. This is x to the 1, and x to the 1 we don't bother to write. And then let's differentiate this 3x separately. So let's do that. That's going to be x to the 1. So 1 times 3 is 3, and this becomes x to the 0. Now we know that x to the 0 is 1. So 1 times 3 is 3. So our answer for this one, dy by dx, is going to be 2x plus 3. Let's try just one more of those. So let's try something harder. Let's say we've got y equals 6x cubed minus 4x plus 3. And I want to find the gradient here, so we're going to work out dy by dx. 3 times 6 is 18, x squared, minus here, so this is 1, 4 is 4, and this one here has no value of x. So because it's got no value of x, then it just disappears, and we're left with our solution 18x squared minus 4. Sometimes when we do differentials, we can use function notation. Here we can say that y is some sort of function of x. If we go back to doing our differentiation by first principles, then that means my coordinates of px, y is going to become x and some function here of x. If we work out the coordinates of q, which were going to be x plus a small amount of x, y plus a small amount of y, this is going to become, if we put it into function notation, x plus delta x and some sort of function of x plus delta x. The change in y, delta y, is going to be a function here of x plus delta x minus some sort of function of x. So delta y over delta x is going to be some sort of function of x plus delta x minus the function of x, all divided by delta x. If we work out what dy by dx is going to be, that's going to be, as we approach the limit of delta x tending to 0, of the change in y over the change in x, this is going to become the limit as delta x tends to 0 of some sort of function of x plus delta x minus my function of x all over delta x. And we can write this often as f prime of x. So we can see that when we differentiate Sometimes they'll give you y equals some sort of function of x, and they will ask you for, can you find dy by dx, or they may ask you to find f prime of x. They mean basically one and the same thing. They're not really any more difficult than that. So this is, if you like, the definition of the function of f of x of the derivative dy by dx. And this thing is quite handy to try and remember, given that y equals some sort of function of x, its derivative, or in other words, its rate of change of y with its respect to x is going to be defined as dy by dx is going to be the limit as delta x approaches 0 of f x delta x minus the function of x over dx. Can we do any other standard differentials to work out x? Yeah, of course we can. Let's suppose we've got some other nasty equation, and they're bound to give you something horrible in an exam to try and do. And you might get some other crappy function, like perhaps one looks like this. This is our function of x is going to be 1 over x. And let's see if we can try and differentiate this from first principles. There we are, off stage, I sharpened the pencil. We've got 2 points. We're going to have P and we're going to have Q. We've got our triangle, just as before. And you can see that if we've got this right-angled triangle here, it's going to be basically the same idea. So let's see what we can do. We know that delta y over delta x, this is going to equal my function of x plus delta x minus my function of x all over delta x. Let's see what we've got. Well, I've got my function, which is 1 over x, so this is going to be 1 over x plus delta x minus my function of x, which is 1 over x, all divided by delta x. Let's now subtract these, and I want to try and get some common factor here, and that's going to be x times x delta x x times x plus delta x is going to be my factor, and I ask, what am I doing to this to get that? So this is going to be x minus, multiply this one up, which is going to be x plus delta x.
Here's your reminder.
And all that is going over delta x. Well, let's try and do a bit of tidying with this. So if I'm dividing by that, I could write that one out as x minus x plus delta x over x plus delta x divided by delta x over 1, and if I'm changing that to be multiply, then I'm going to multiply then by 1 over delta x. That's going to give me then x minus x plus delta x over x times x plus delta x times delta x. And that is going to become minus delta x over all this lot and we can cancel these, which is going to give me minus 1 over x plus delta x times x. So as the limit of delta x tending to 0 is become here dy by dx becomes equal to minus 1 over x times x, x squared. So the derivative of y equals 1 over x with respect to x is going to be 1 over x squared, and it's going to be a minus. There we are. I hope that's given you an idea about differentiating from first principles. Typically they like to put one of those questions up in the paper to try and get you to differentiate from first principles, and it's going through that process, trying to write it all down, trying to keep it as simple as possible, to try and put down every stage so that the examiner can see that you know what you're doing. Until next time, when we'll have a look at a bit more maths, I'll see you then. Take care.